Hello and welcome to our lesson today. The first part is pretty straightforward. You're just reading definitions, but the second part is stoichiometry, which we did do back in grade 11 chemistry. But I know stoichiometry can get a little bit confusing, so I just wanted to run through the PowerPoint with a video. Plus, if we were doing this live together, I would have shown the example differently than I have it in my PowerPoint notes. So I just want to go through and explain a little bit because I think the second part might be a little bit confusing to just try to learn by reading. Okay, so the first part of this lesson is pretty easy. We should know what a reaction rate is. We learn about reaction rates, instantaneous rates. We know how to do the graphs and to get all that information from a graph. Now today's lesson, we're taking a break from the graphs just for one day. We're going to look about how do you measure reaction rates. We learned how to calculate reaction rates from data and from a table and from a graph, but now how do you measure it? So there's three different ways we can measure reaction rates. If a gas is produced, then it's pretty simple. You just collect the gas and measure the volume and or the pressure. So that's a pretty easy way to see how fast or how slow a reaction rate is going. So gases, we've done some reactions where you produce a gas, the zinc and hydrochloric acid, and you saw the bubbling. So when a gas is produced, if you can collect the gas in a separate container, just collect it and measure the amount of gas produced. And that's pretty easy. The more gas produced, the faster the reaction. The less gas produced, the slower the reaction. So that's pretty straightforward. Second one is ions. So the conductivity of the solution changes as ions are produced. So that one we didn't do in high school, and you won't do it at university. I think that picture's a little bit blurry, but you would need special equipment where you just connect it and it measures the conductivity, and it would just show you when there's different amount of ions. So we don't have that in the lab because I feel, well, for one lab, in one class, it's probably not worth it. So if you go into university in your second, third year level chemistry courses, you might actually use equipment like that. But again, just as you have different amounts of ions produced, then the conductivity of the solution changes. And that would be another way to measure rate. And the third and final one is something called a color change. So we've seen color changes in the lab, but if you actually use something called a spectrophotometer, again, we don't have one in high school, I don't think it'd be worth the amount of money to spend for one lab that maybe one class did. But if you go into university, I know I was in the course I took was called Chemistry of the Main Group Elements. Yes, that is a course I took in university, and we were in the lab a lot, and we used the spectrophotometer a lot. So right now, if I just said, what are the colors, you would say yellow, orange, pink. But if you use a spectrophotometer, it puts it in. It's really neat. You put the vessel in and you press it, and it actually tells you the actual wavelength. So we did look at the scale. We know that every color has its own unique wavelength. So a spectrophotometer changes it. So our eye, maybe all the solutions look pink to us, but if you put it into the machine, it would tell you the exact different wavelength of that color. So again, those are three ways just to measure the rate of reaction, how fast or how slow things are going. That part's pretty straightforward. Then here comes the stoichiometry. So that is the Haber process. We talked about the Haber process in grade 11 chemistry. I showed you the video about Fritz Haber, the scientist who came up with that, and how he was a very divisive person. He was brilliant. This reaction has saved millions, billions of lives because that's how we do fertilizer for food. But his chemistry knowledge, then he extended that to help produce Cyclone B, which was used in the gas chambers in Auschwitz in World War II, and we know how that ended. So was he good or was he bad? We watched that video last time. But so that's the Haber process. We use it a lot because it's a nice simple one, and for stoichiometry, it's not a 1-to-1 ratio, it's not a 1-to-2 ratio, everything has a different mole ratio. So you have 1 mole of nitrogen reacting with 3 moles of hydrogen to produce 2 moles of ammonia. So it's a nice easy one to work with in stoichiometry. So this just shows you the rates. Oh, again, just to be clear, the reactants are on the left, so that we say that the reactants are used up or consumed, and then the products on the right are produced. So this is the language we use. The rate of production, it's a product, so ammonia is being produced, and then nitrogen and hydrogen are the reactants. They're being consumed, used up. So just want to clarify the language of that. Now, in the notes, we use the Haber process to calculate this. I have done the work on the active inspire that I'll switch to. I'm doing the same method, but I feel like I'm basically doing the mole ratio method we learned last year. So I've just skipped some steps. So I'm going to solve this question, but on the active inspire. So for this one, we tell you what rate that hydrogen reacts at. It reacts at a rate of 1.5 moles per liter second. So we've told you our reference point is hydrogen. Hydrogen is reacting and getting consumed at a rate of 1.5 moles per liter per second. So based on that, how fast is nitrogen being used up and how fast is ammonia being produced? So I am going to switch now to my active inspire. So hopefully, that's set up. So this is the same way that I solved in the PowerPoint. I just was missing some steps. So the full version, I would go back to grade 11 chemistry. How many moles of liter of nitrogen is being used up when the rate for hydrogen is 1.5 moles per liter? So just like we did in grade 11 chemistry, what's the rate of nitrogen if we know the rate of hydrogen? And then where did I get these numbers in the denominator? Well, I used it from our balanced equation, stoichiometry. In the balanced equation, we know 1 mole of nitrogen reacts to 3 moles of hydrogen, so then the rate would be 1/3 of that. I know if you can see the mole ratio, you don't have to do the full version. Some of you were mental mathing it on your test, but still show me that step. So then you cross multiply, which is what I did in the notes, 1 times 1.5 divided by 3. So that's how you get the 0.5 moles per liter per second. So I just didn't show the full equation in my notes, which I would have if we were all together live. Then in part B, they ask you, what's the rate of ammonia? Now that's a little bit harder because in A, it's a 1:3 ratio. You can mental math it, but here it's a 3:2 ratio. So that's a little bit harder to mental math. So again, the rate of hydrogen is still 1.5 moles per liter per second. So then what's the rate of production of ammonia? Again, what's the rate of ammonia compared to the rate of hydrogen? Where did these numbers in the denominator come from? Oh, stoichiometry, the balanced equation. We know from the equation 2 moles of ammonia react with 3 moles of hydrogen. So cross multiply 1.5 times 2 divided by 3. That's how you get the 1 moles per liter. So I start my notes here. I don't show this opening step, which if we were together we would. So I just wanted to give you a little bit more work to show where these steps and these numbers came from for stoichiometry, because I know it can get confusing. Okay, and then the last one is entirely new concept. We've never done this before. The answer is in your notes, but I did want to write it out together, discuss it, because I feel like if you're just trying to learn by reading, it's like, well, what do all this means? So now, this is different. So the next question says, write the rate expression for the Haber process. Now, we look, it's not a 1:1:1 ratio. They don't all act at the same rate. So you don't produce ammonia at the same rate that nitrogen gets used up. Nitrogen doesn't get used up at the same rate that hydrogen does. They all are at a different rate. So for the rate expression, we want to make all 3 of these equal. How do you make all 3 rates equal when they're not? So this is how we do it. So it's the change in concentration, square bracket means concentration. So the change in concentration of nitrogen. And again, I'm skipping out some steps, so you've got the full answer there, but I just want to show, I'm purposely leaving out some things to deal with it. So the rate in the change, delta means change, the change in the concentration of nitrogen to the change in the concentration of hydrogen, to the change in the rate of the concentration of ammonia. So right now, this equation says that all 3 rates are equal. They're not. So we need to add some things to make that statement correct. First of all, anything that gets used up, we put a negative sign in front of it. Because if you're getting used up, it will be negative. Here, it just stays positive. You could put a plus sign, but if it's positive, there's no need to. So that's the first thing you need to add to your equation. Anything that's a reactant will get a negative sign in front because it's being used up. Anything that's a product stays positive. Okay, now, we've learned in our previous lessons, rate is change in concentration over change in time. So now I'm going to put change in time, delta T, change in time, delta T, change in time, delta T. So we've accounted for the difference that some are used up and some are produced with the negative and the positive signs. But now the change in time, it's not the same time. They don't have the same rate. It's not the same mole ratio. So because they're not equal, we're trying to make these rates equal. So we have to account for the fact that they're not at the same rate. So we have 1 mole of nitrogen reacting to 3 moles of hydrogen, reacting to 2 moles of ammonia. I didn't put the 1 in my notes because we know a coefficient of 1 you don't need, so that's why I left it. So that's how you do it. So hopefully that helps a bit. Otherwise, if you're just trying to read that, I'm like, it's all Greek to me, and it literally, delta is a Greek letter, haha. Okay, so hopefully that explanation helps. So then going back to the PowerPoint, so your assignment today, while we're in the lab, so like I said, next day is lab. I'm alternating so we can do lab 7. So while one group is in the lab today, the other group is at home. I'm doing kinetics assignment number 2. It's all directly from today's notes. So if you look at today's notes, you should get the answer, or it gives you the examples of how to solve for them. So you're doing some questions about rate, measuring rate, and then some stoichiometry. Plus I posted the answer key there to help you. But like I said, if you need help, the next day we're back, or you can always send me a message on the Teams chat function. So good luck with that worksheet today. And what is a chemist's favorite plant? Stoichiometry. Same joke from last year, grade 11. If you didn't laugh, Len, well, now's your chance to laugh in grade 12 at the stoichiometry joke. Okay, so good luck with the worksheet today. Like I said, if you're at home doing the worksheet, then the other group, you're with me today doing the lab and actually collecting data. Okay, good luck.